It's rolling. It's Thursday, November 6th. You're gonna work on these puzzles, so chapter 7 and 8 from your book. Just whatever we do in class, I'll just have you guys turn is to the gray tray. So just make sure that you attach your work. So everybody has paper, and everybody can turn in these puzzles at the end of class, and then I'll be scoring those tonight and I did print out some FRQs, so I'll get those to you guys tomorrow. We'll do some FRQs, do that. And then yesterday, you guys got a take-home quiz. Everybody did get an energy take-home quiz, right? Right, so that'll be due on Monday. I have not passed the last quizzes back yet because not everybody's turned it in. I know that. Okay, so highlight some ahead of time. We thought would be pretty good. Right, so number 7. Got a catcher in a baseball game stops a pitch. Ball originally moving at 44 meters per second. Guys, 44 meters per second. That's pretty close to 100 miles an hour. From the moment it first came in contact with the catcher's glove. After contacting the glove, the ball traveled an additional 12.5 centimeters. There it is. 12.5 centimeters before we can completely stop. The mass of the ball is 1.5 kilograms. What's the average force that the glove imparts on the ball during a catch? Don't worry about the comment below. So I think I'm gonna here. If you guys can always stay a step ahead of me, then that would really be the best thing. But we've only got so much class time, so I'm just gonna go along here. I would think of this as an open system. So I think this ball starts off with what kind of energy? Yeah, kinetic energy. And then I would finish this off like this. I think minus the work done by the glove brings it to 0 joules of energy at the end. Like something like that. And the height of the ball and the height change would probably be relatively insignificant compared to right, the motion of the ball. So I think it's a pretty good simplified way to think about this. So 1/2 times the mass of the ball times the initial velocity squared minus the force from the glove times the stopping distance goes to 0. So that it's a back picture, right? Guys following step by step. Again, like always, if you stay a step ahead of me, that'd be really good. And I think the question was, they did say what's the average force, right? So if it varied at all, great. So we're going to treat this as like a constant value going across. I'm thinking something like, here it is, right? Something that's like this right here, right? There's a constant force for some distance. You can do some work. Now it would be, if the ball's moving forward, you guys think the glove's pushing the other way. So really this could be like an upside down graph, like a negative force kind of thing. You guys see that? All right, so for subtraction. All right, let's solve in terms of variables first. Okay, do that. Kind of add this over and divide by d. So force from the glove would be, let's see, 1/2 mv squared. So mv squared over 2. And then we're going to eventually divide by d. So squeeze a couple of algebra steps there. Let's go and plug in some numbers. So mass of the ball 0.145. That's kilograms. The speed of the ball, they did give you in metric units, meters per second, it's at 44, 0.0 meters per second, which makes me think your textbook's probably looking for 3 significant figures. Like now speed squared, don't forget that. And then, well, stopping distance, guys, 12.5 centimeters. Can I just put 12.5 right here?
No, because it's going to be meters.
It's got to be meters. Guess how many meters is this? There you go, 0.125. Meters. Yeah, there. Okay. So it's got to be meters, how many meters. Now make sure you can correctly plug this into your calculator. In the calculator, I would do one more thing. I would throw in some parentheses all around this denominator. Because if you don't do that, it's not going to calculate it right. They can turn around, multiply by the distance, and give you something totally wrong. So make sure that you can correctly plug that in the calculator. Let's make sure we're all getting the same number here. All right. I'm getting 1123. Are you guys getting that number on your screen? Right there. Okay. So 1,123. And what's the unit?
Joules.
Not joules.
Okay,
Newtons. Yeah. Because we're talking about force. Right. The force measured in newtons. Really, maybe the best one to say is like 1120. If you're allowed to have three significant figures. Right. You could also write that in scientific notation. You write 1.12 10 to the 3 newtons. Okay. See, 1,000 newtons. Well, I know your largest lab weight weighs about 10 newtons. So to get to 1,000, you need what, like 100 of these? Right? Right. Now that's a very tiny time interval, but can you guys imagine if there's like a big old bag of 100 of these? Yeah. Um, it would feel about that amount of force again over a very small time interval, which wasn't really addressed here. You know what? Let's address that too. I wonder how much time it would take to bring it to a stop. How much time? Do you think you guys can calculate how much time? Huh? How did you do that? What's the way to do that? Kinematic. I like that. Yeah, yeah. So see, the ball's going to rest. Or actually, we do want time, right? So let's not do this. Um, see. Actually, you know what? We do have to get the acceleration ball, don't we? Yeah. Right. So here, maybe I'll just go this verbally. Right. So ball's going to rest from 44 meters per second, and then it stops over 0.125 meters. So you could calculate the acceleration first, right? You could do that. Yeah. Once you have the acceleration, you go to either of these top ones, probably this middle one, and then solve for the time. You could do that. Makes that. Okay. No, I'm not going to do that just because we only have so much class time, but at least you see how to do it. Okay. Okay. And if you have some force acting over some time interval, that actually links to what we're going to get into next week, which is momentum and impulse, which is all those standards over there. All right. Number 8. The graph below shows, force versus position. Guys, as soon as you see force versus position, and you're going to see these graphs on the AP exam, you should probably guess what question is going to come up. Well, maybe. Okay. So it's probably something to do with like work and energy. Because what property of this graph tells you work?
The area.
Yeah, the area under the curve. I see a trapezoid there. I see a negative trapezoid there. Ooh. Could a positive trapezoid be like you're doing positive work on something, and then the negative trapezoid you're like taking energy out of the system? Yeah, that's how I would interpret that.
I bet.
Okay. So we got a low friction cart. Ooh, 500. Hey, 500 grams. Actually, that is exactly what your guys' low friction carts are. They were half a kilogram, weren't they? Yeah. See the speed of the cart at position 0 is 0. So it does start from rest. They do have to specify that because otherwise you wouldn't necessarily know that, right? Just from the graph. Calculate the velocity of the cart after 1 meter, which brings you up to right there. Isn't that the 1 meter mark? I'm stopping right there. Okay, so I see could that be like a skinny triangle next to a big old rectangle? Right. And then the velocity after 3 meters. Okay, so let's do one thing at a time here. So it starts from rest. I'm gonna write this phrase: work, energy, theorem, which says that the work you put into something goes into it. It's kinetic energy. Now, really, this only works if there's no height change, so there's no energy that diverts into potential energy. Right? There's no springs. There's no friction. But that's exactly what we have. So I think this applies right here. About work. Right? And in this case, the work is the area under the curve. That's going to go into, well, 1/2 mv squared. So let's find out. Okay. If you go up to 1 meter, that would be, looks like these intervals go 0.2 meters at a time, like 20 centimeters. So I think this triangle right here, if I split up this triangle, does this have a base of 0.2, 0.2, is that 0.4 meters right there? That'd be 0.4 meters, wouldn't it? Okay. And a height of 8 newtons. So I'll label that 8 newtons. And then this rectangle next to it, can I split this up too? Okay. Guys, what's the width of this rectangle?
6.
Yeah, I think it's 0.6, right? 0.6 meters. And it has the same height, also 8 newtons. Okay. So, okay. Okay. So if you guys see it, this total base is 1 meter. They split it up into 5 parts. Okay, so that's got to be 0.6 meters right there, right? Yeah, the height's 8 newtons. All right, so let's find the area. So that would be, so for the triangle, it's 1/2 base height. So 1/2, 0.4 meters, a height of 8 newtons. And then plus that rectangle next to it has a base of 0.6 meters and a height also of 8 newtons. Doesn't that represent the total energy in the system? And that's all going to go into 1/2 of v squared. Here, since I'm plugging in numbers, I'll just go ahead and keep doing that. We have a cart mass of, guys, what should I put in for the mass? What number? 0.5, because it has to be in kilograms. Okay. And that's some speed at that interval squared. So this is for part A. Just the part A. Guess that. All right, guys get that?
Yeah.
Okay. All right, so that's 0.5 times 0.4 times 8 plus 0.6 times 8. All right. Here, I'll throw in the middle step. How much energy are you guys getting in the system altogether?
6.0.
Yeah, I'm getting 6.4 joules also. Yeah, works out. That's a good sign. And let's all multiply. Well, yeah, I've got multiplies. Okay, you got that. All right. Then divide over and take square root. V equals. Right, I have a number on my screen. Who else has a number? Yeah, you're good. Yeah, same thing. Okay, so if you guys tell me 5.06, pretty good. 5.06, that'd be meters per second. Okay. Okay, so take this energy, divide by this half mass value, then take the square root. You should get that speed right there. Okay. Oh, right. Here, just to save time, here, we'll just go to the rest of this part B verbally. Okay. So if you want to take it all the way out to 3 meters, which is the entire graph, could you find the area of this big trapezoid and subtract this negative subtract this? Okay, so they subtract from each other because one's positive, one's negative. So there's still net energy that went into the cart. Okay. And then you just follow the same process from there, right? You guys can do that. Right. Number 12. Earth orbits the sun at radius 1.5 times 10 to the 8 kilometers. At this distance, the force of gravity on Earth due to the sun is 3.6 times 10 to the 22 newtons. The Earth's orbit is perfectly circular, which it isn't, but it's fairly close, so we're just approximating where it. How much work does the sun's gravity do on Earth in 1 year? Ooh, this is more of a, well, what do you guys think? What do you guys think about this one? Huh? Do you guys remember work is a dot product, force distance? Right? And guys, dot product means what about the force of the distance? If the components that are in the same direction, right? Yeah, so carrying something up the stairs, they'd have to, it's both the vertical components. But if you're pushing a shopping cart forward, it's both the horizontal components. It's whatever components are in the same direction. So if you look at the angle between the two vectors, then it always turns out to be a cosine of that particular angle. Okay, so it's normally written as a cosine definition for that. Okay. But it's a dot product. Well, guys, if you have, here, I'll draw this up. The sun, right here, okay, you got a planet going around, okay, and the orbit is pretty well circular. Okay. And the force from the planet, the force from the sun on the planet, is pulling straight in towards the center, force due to gravity. And the motion of the planet, the instantaneous velocity, is perpendicular to that. Well, guys, how much of those two components is aligned in the same direction? Yeah, nothing, zero. Yeah, nothing. Right. So, does the sun actually do any work on Earth? No, zero. The answer is 0 joules. 0 joules. Right. There's some similar situations. So, what if you have a ball on a string? Ball on a string, right? And the string's going around in a circular path. Around a circular path. Okay. Guys, how much work does this string do on this ball? Yeah, 0 joules. 0 joules. So this could be a closed system. Now that's regardless of if it's in a horizontal circle or a vertical circle. 0 joules. The string does 0 work on the bottom. Which actually reminds me of one of your take-home quiz questions, number 10, where I give you a ball on a string going in a vertical circle. Actually, I did want to throw you guys a hint on this one because this is a pretty tough question. I was thinking, should I leave this one on here? Should I swap it out for an easier one? I'll leave this on here. I'll really challenge you guys. So we got a ball going in a vertical circle. Here, I'll please throw you guys a hint. Okay. And it's saying treat this as a closed system, so that the ball Earth system remains constant. You guys notice how I define that system, the ball Earth system? I didn't even include the string, but I don't have to because the string does no work on the ball, right? It provides a force on the ball. It definitely affects its motion, but the motion of the ball is always perpendicular to the pull of the string. So the string technically does no work on the ball, right? So I can call that a ball Earth system. I can treat that as a closed system. If that's a closed system, the ball Earth system is a closed system. Okay? Is the ball going to speed up as it goes from the top to the bottom? It's going to go faster, faster, faster? Yeah, okay, because Earth's gravity is pulling it down. Okay. So in terms of energy, you can say it's losing potential energy, it's gaining kinetic. And then once it crosses the bottom and it moves back towards the top, is it losing kinetic, gaining potential? Yeah, so it's losing 1/2 mv squared and it's gaining mgh. Hence, it would be slowed down. Okay. So it's going to speed up, slow down, speed up, slow down. Okay, so just cyclical, right? So like that. So now it varies, right? Now, I love this really big. I did not give you any numbers here. Like, as in, I didn't give you any specific speeds. I didn't give you the mass of the ball or anything like that. Okay. The question is, if you look at the tension in the string, there's a tension on the top side and there's a tension on the bottom side. Now, do you guys think that those tensions would be different for the scenario? The tensions would be different. Which tension do you think is bigger? The tension when it's going to the bottom, or the tension when it's going to the top? Bottom. Yeah, definitely bottom. The tension's gonna be more. Like you could definitely see it if you had a spring scale. Okay, what if I threw a spring scale like right in the mix here? Okay, when the spring scale, do you think the spring scale rating would be maximum when the ball's at the bottom?
Yes.
Okay. Yeah, it'd be kind of smaller at the top. So the question is, what is the difference between those two tensions? That's exactly the question. And I gave you multiple choice, and it turns out that that difference in tension is some exact multiple of the weight of the ball. So your 4 options are some multiple of mg. You guys got that? Yeah, is that? Okay. Now, since this is circular motion, part of this to be able to answer this does take back to a couple of weeks ago, where you have to think about circular motion. So here, help you guys out here too. Let's look at let's do a free body diagram of the ball here, a free body diagram of the ball here. Okay, let's get you guys going. So let's start at the bottom. What force? What's one force in the ball at the bottom? Yeah, it's weight, mg. So I'll call it mg. And what other force? Attention. Attention. Right. Yeah, there's no surface, so there's no normal, but there's attention. The attention's pulling up. Now, I'm not going to claim that my drawing's to scale. Right? In fact, it probably isn't, but would the tension have to be much greater than the weight?
Yes.
Right. That definitely has to be true. I'll call it F sub T bottom. The tension at the bottom. Okay. Okay. Guys, how do you know the tension up has to be more than the weight down?
Or also file.
Because it's moving on a curved path. And because something moving on a curved path has to have the what force acting on it? Centripetal. And what is the centripetal in this case? It's the difference between these two. You see it? Centripetal force would be the difference between these two. Okay. So here, got some sideways velocity. Okay. So I'll say, just to remind you guys, centripetal force, well, I'll say at the bottom, equals the tension at the bottom, yeah, minus the weight, because they're acting opposite direction. Right. But when the ball is at the top, does it still have a weight acting on it? Huh? Yeah, it's still got weight. Is it the same weight? Is it the same weight as before? Yeah, same weight. Same weight. So that's the same. Same energy. Right. Does it still have a tension acting on it?
Yeah.
Probably. Does it have to have a tension on it?
No.
Not necessarily. I did throw that as a hint, although maybe it's not the most helpful hint I've ever given you. It said the minimum speed at the top of square root GR. You guys remember that from the cup of water? Right. Now, that specific case is when it has zero tension at the top. Right. That doesn't necessarily have to be the case, though. Okay? And whether that is the case or not, that multiple choice answer I gave you guys is still the same. Right? Whatever the answer is, that doesn't change. Okay? So maybe I included tension up here, or maybe I don't. And if I do, maybe it's larger than the weight or smaller than the weight. Right? And that's ambiguous too. Depends how fast you're spinning this around. Right? So I'll go ahead and draw attention. I'll say F sub T top. Okay. Now at the top, ooh, I do see that both vectors are pointed in the same direction. Could you guys say that the centripetal force at the top equals the sum of these two? Well, here, I'll try to match this. So F T top plus mg. Right? Ft top plus mg. Isn't that true? Because they're conspiring together. Ah. And finally, one more hint on this. You guys know an expression for centripetal force is what over what? mv squared over r. Actually, you know what? I said one more hint, but maybe I'll give you guys a little bit more. Guys, what's the total height of the circle in terms of its radius?
It's like. With the height is like 2.
Yeah, two R, right? 2R.
Okay.
So what's the potential energy at the top compared to the bottom?
Okay, I got rid of it.
Well, potential energy at the bottom
That's
is 0 joules. Yeah, mgh, and h is 2R, so it'd be mg2R, wouldn't it? Is that? Okay. And the speeds are different all around. Okay, but does it have some kinetic energy both here and here?
Yeah.
Yeah, it has some kinetic energy here and here, but it's different amount of kinetic energy. But what can you say about the kinetic energy plus the potential energy everywhere? Constant, because it's a closed system. The Baller system is a closed system. Okay. Okay. So there's a bunch of little parts lying around there. Okay. Now you can solve this in terms of variables. I tried it a few different ways, and I always got the same answer regardless. Okay. If you get really bogged down, guys, could you just make up some numbers like, you know what, I just want to use a 1 kilogram ball, and I want to use a 1 meter like string, and I want to have it go around this fat. Could you make up some numbers? You totally could. Okay. You'll still get the same correct answer. Okay, so there's some hints on what I think is probably the hardest question on your take-home quiz. All right. Number 13. An ideal spring with spring constant 8 newtons per meter is fixed at one end of a wall, the other to a low friction cart with 750 grams mass. Initially, it rests on a horizontal table. The student moves the cart distance of 0.5 meters, stretching the spring and holding it at rest that position. What's a graph of the force on the cart as a function of spring distance, and calculate the work done and potential energy stored. And then we're going to release the cart for rest. What's the speed of the cart is going through the equilibrium position. Okay? And so I'm going to give my best interpretation of this, or my best interpretation. Okay? So we got a wall. We got let's say a really long table. Okay? So sometimes like catch this in. Okay. They said low friction, so there's no friction. Okay. And let's say I have a fairly long spring. Okay, so I got a spring. Okay. And we'll call this position 0 right here. This one guy. So this is I'll call this position 0. 0 meters. Okay. All right. Then we're gonna take a cart and so this say stretch it. Here's the distance. Well, I'll say he stretches it. Okay. Right, let's say you attach this to a cart and you stretch this an additional like some amount. Let's bring it up back here. Okay. Low friction cart. Okay. All right, so this distance here is at 0.50 meters. Like that. Okay. The mass of the cart is 0.75 kilograms, and the spring constant here, I'll call it K, is 8 newtons per meter. So we got all that. Okay, I think that's the whole setup, isn't it? Yeah. Okay. So part A, sketch a graph of the force exerted on the cart as a function of distance moved. Right. They say from 0 to 0.5, but here I do want to go ahead and extend that to a fuller situation. Because guys, after you let go of this cart, doesn't the spring pull the cart back towards the center?
Yeah.
But guys, when it gets to the center, it has a lot of what kind of energy? Kinetic. So is it going to overshoot the equilibrium and push the spring into compression?
Yes.
Guess how far it's going to go?
0.5 meters.
0.5 meters on the other side. Yeah, make 0.50 meters. Okay. Yeah, you can get that by symmetry. You could also think that in terms of energy, because right here there was energy. Isn't the energy all stored in the spring at this point? However many joules that is, right? In terms of like stretching for tension. But if you put the spring into compression, it still follows, Hooke's law, just go the other way. F equals kx and so on. So it could be the same amount of energy could also get it there. And if there's no frictional loss, it could just oscillate back and forth between those two positions forever. Okay. So let's do force as a function of position. I'm gonna make a graph looks kind of like this. So what's force in newtons as a function of position? And did I do this wrong? Actually, I should open this way up like this. Okay. Position in meters. Okay. Because we're going to go to 0.5 meters, but we're also going to go back to negative 0.5 meters. Okay. And then the force, well, yeah, we haven't used Hooke's law in quite a while, but you guys know Hooke's law, right? That talks about forces in spring. The spring force is what?
KX.
KX. Yeah. Actually, which force did they talk about? Did they say the force on the spring or which force? Force exerted on the cart by the spring. Okay, guys, if they said the force exerted on the cart by the spring, guys, if you pull the cart in a positive, now, I'm getting kind of technical here, but this could come up. If I pull the cart in a positive direction, which way is the spring actually pulling?
Back.
In the negative direction. So I'm going to indent Hooke's law over here. Hooke's law. How do I have to indent Hooke's law?
Negative.
Yeah, throw in a negative. Okay. Actually, a lot of textbooks just go ahead and throw that in anyway because they talk about the force of the spring. Okay. So let's figure out a value here. I'll say Fs max. Now, okay, got a negative. I got 8 newtons per meter is my spring constant. They gave that here. And this goes to 0.5 meters. Put it all together. Guys, is that negative 4? And what's the unit? Newtons. Yeah, because we're talking about force. Okay. So this is something that you guys do probably a couple months ago, whenever you learned Hooke's law. So a long time ago. Okay, so that's Hooke's law right there. And so I'm going to scale my graph up to 4 newtons and down to negative 4 newtons. Okay.
This is like a
Now, when you pull it to half a meter, it's the spring's pulling back the other way, so that's this point right here. Okay. And then, guys, at the equilibrium point, how much force is on the moving cart? Yeah, 0. And when it goes into full compression on the other side, is it just the same values, just flip the other way?
Yes.
Wow. So I think that would look like just like that.
Diagonal.
Yeah.
You can tell me, what is the slope of this line equal to?
No.
About 8 newtons per meter. Yeah, you say negative. Okay.
Negative 80?
Yeah, negative 8 then newtons per meter.
What?
Is that's Hooke's law. F equals kx. Here's F. Here's x. The slope is k. That's the spring constant. Okay, that's good. Use the graph to calculate the work done on the cart by the spring, or you could say the work done stretching. It's the same amount of work. Right, so how much energy did it take to stretch it out here? Wouldn't that be the area between the curve and the axis, which would be here? I just hashed in this triangle right here. Is it the area of that triangle?
Yeah.
Ooh, guys, is the area of that triangle equal to 1/2 kx squared? I bet it is. Now let's try it both ways. Let's find the area of that triangle. Let's do also this 1/2 kx squared, and I bet it's the exact same value. Let's make sure if you guys see that. So part B, the work done by spring, or the energy stored in the spring. So let's do 1/2 base height. So we got a base of 0.5 meters and a height of, well, I'll just call it 4 newtons. Okay. So half of 4 is 2, and point times another 0.5 would give you one what? Joule. Yeah, 1 joule. The answer should be 1 joule. But you say 1.00 joules. Or if I do it the other way, and I go through the expression 1/2 kx squared, that'd be 1/2. I have a spring constant of 8 Newton per meter. I'm stretching at 0.5 meters, and that being squared. Oh, guys, what's 0.5 squared? Is that 1/4? And then times another half is 1/8. What's 1/8 of 8? It's 1 joule. That's the same thing. You guys see? Comes out the same thing. So no matter how you do it, there's two different ways of doing it. Get the same answer. And then the cart's released from rest. Calculate the speed as it goes through the equilibrium position. Speed through the equilibrium. Okay, so, well, here's exactly how much energy is always in this closed system. We always have 1 joule of energy to work with. So part C, can I say sum of energy initial equals sum of energy final? Okay. It's always 1 joule. So we're going to say 1 joule equals, and then 1/2 mv squared. So, I should have asked you guys, going through the equilibrium position, there's no energy in the spring, there's no height change, so all the energy would be kinetic, wouldn't it? Okay, you guys really stuff. So 1 joule equals, now we have a 0.75 kilogram part. And then we're solving for V. Okay. Well, I'm writing out a paper here, but you guys can do the algebra, right? So times 2 divided by 0.5 and then take the square root. So I'll do the algebra on my calculator. Let's see if we all get the same thing. So last step's gonna be a square root. You take 1 times this 2 divided by this 0.75. I'm getting a speed, and this would be the maximum speed, so if they couch the question that way. 1.63. What's the unit? 1.63 what?
Meters per second.
Meters per second. Aha! The speed.
Per meters.
You guys got that? Number 19. Got gravel-filled runway truck. Oh, I'm sorry, runaway truck lanes are designed to stop trucks that have lost their brakes on mountain grades. Yeah, I remember driving across the country. If you've ever been to mountain regions or like hilly regions, sometimes you'll see like a lane off the highway that was just like a long bladed gravel. Right? So yeah, if you have like a big old semi truck and its brakes go out, it can just kind of scoot down that lane. Central lane is horizontal, over uphill, and about 35 meters long. We can think of the ground as exerting a friction force on the truck. Right, also gravel, you could sort of simplify it that way. Let's say the truck enters the gravel lane with a speed of 55 miles an hour, so regular highway speed. Now, very conveniently, they did convert that to metric for you guys. But, oh, by the way, it's about 24.6 meters per second. You guys see that? Here's a good rule of thumb. If you take the speed in meters per second and you double it, and then add a little bit, that'll get you to the speed of miles per hour. Or you can go the other way. Take miles per hour, do half and subtract a little. You get pretty close to use the work energy theorem. Oh, work energy theorem. Hey, I wrote that out earlier. To find the minimum coefficient of kinetic friction between the truck and the lane to be able to stop the truck. If the lane is horizontal. Because up here they said, well, a lot of times these are angled uphill a little bit to further help the truck come to stop it. What if it's just straight horizontal? Yeah, so we do that. It sounds like a braking distance question.
Oh.
Let's go horizontal. Got this truck barreling down. Have to stop. So we've got some distance to work with.
You don't have brakes.
Let's say this distance is, let's say, 35 meters.
Did you start this conversation?
Ooh, 35 meters. That approximately a third of a football field. Do some in there. Yeah. 24.6 meter per second. Gotta bring this to a stop. I think that's all I told us. Oh, they never gave us the mass of the truck. Do you need the mass of the truck?
Probably not.
No. Makes no difference.
Because mass ejector is full.
Right. They said work energy theorem. Can you guys set up an expression that looks like work energy theorem to bring this truck to a stop? Here, while you guys are doing that, see if I can dig up the poster on this one.
So seeing things we don't know.
There it is. Did you guys come up with this expression right here? Here's work energy. Starts off as 1/2 mv squared minus work from friction. It goes to 0. Okay, based on like these top 2 lines, something like that. Right. And then if it had been angled uphill, that could further help it bring it to a stop because some energy would be converted to gravitational potential. But we don't have that in this case. So I'm gonna say initial energy or initial kinetic energy minus the work done by friction goes to 0. So 1/2 mv initial squared minus friction work done by friction. That could be what times what? Force times distance. So friction force times stopping distance
Force, yeah.
goes to 0.
That's right.
This would be joules. Okay. Yeah, you guys know I'm basically recreating that poster I just splashed on the screen.
Yeah.
But that's good to go step by step. So 1/2 mass of the truck, initial speed squared minus. Okay, now here's where we're going to do a big old substitution on this friction force. Well, we got to go back a few weeks ago in this class. So let's do a free body diagram. Let's make a free body diagram on this truck. Guys, what's one force on this truck? It's weight. Yes, so that's mg. What force is holding it up? Yeah, normal force. Hey, for a flat track, is the normal force equal to what? It's weight. Mg. It's weight. And then if the truck's braking to a stop, what else do I do? The friction force pointing to the left. So the friction force. Okay. Now, guys, the whole thing we're trying to solve, the question here is what's the coefficient of friction? So how is this friction force related to this normal force? Yeah, coefficient of friction times the normal force. Would that be true? Maybe I'll call it sub k. Or what? Maybe I'll just leave it as a generic view, but whatever. Because maybe this truck has anti-lock braking or whatever. However you do that. And then this normal force, you guys told me it's equal to the weight for a flat track. So can I further say it's equal to mu mg? Okay, that's what this friction force right here is. That's all okay, right? So I'm going to sub that right here. So instead of friction force, I'll call it the coefficient of friction that we're solving for times the weight of the truck. And then after that, we have multiplied by the stopping distance goes to 0. Right. Is that? And you know what? We're like halfway through having solved it already in terms of variables. So yeah, let's just march on through and solve in terms of variables. I mean, this mass better cancel out anyway because they never gave us the mass. So let's just solve for mu. Can you guys finish the rest of this? Solve for mu. Right, IGD.
I did it.
Somebody got on my poster. Hey, that's what I got on my poster. Oh yeah, look at that. Look at there. It's the same thing. Alright, you guys good? Alright, let's plug in some values. I'm curious to know what is this coefficient of friction? You guys up to date? Any questions so far? Sure. Let's get this ahead. So coefficient of friction is okay. He's at 9.8 by the way. 9.8 meters per second squared per gravity field.
Yeah. That's so exciting.
If wait, oh, hold on. What did no? Yeah, we're good. And yeah, no, we're good. We're good. Right. I was just looking at the thing. And, I was tripping myself out of it. Because I just realized my poster set up for distance, and this is set for coefficient of friction. But you can actually take this and rearrange it, and it would look just like that. So yeah, they're the same thing. Wait, is that right? Yeah, that's right. We should it's the same thing.
Right, Mr. President.
Okay. Here guys, let's play around with some proportions before trying straight to the answer. Guys, what if the necessary stopping distance was shorter? Like, we don't have 35 meters. The mountain cliff is too close. We got to bring it to like 20 meters. Guys, if the distance is getting shorter, would you need more or less friction?
More.
You better have more. You guys see that? If D gets smaller, U gets larger. Vice versa. If you have more distance to work with, we got plenty of distance. We can stretch this out like 50 meters. This could have to, this could get smaller. What if the speed of the speed of the truck was going like way faster than was breaking the speed limit? Do you need more friction? Yeah, maybe that's even more obvious. Yeah. So this is working. I don't know yet. We're trying to find it. Yeah. So some guys are telling me said 0.88. Yeah. You guys see that? We'll find out. Okay. Oh yeah. Oh yeah.
No, man, I can't even 6 and 7. No, good, so good.
What you've done?
I think so.
See if I can fit in one more. Number 18. A small asteroid has a mass of 100 kilograms, moving at 200 meters per second when it's 1,000 meters above the surface of the moon. How fast is meteorite traveling when it impacts the lunar surface and straight toward the center of the moon? And they gave us the radius of the moon in question B down here, so that might be helpful too. And also the mass, that can be helpful. So 18. So we got the moon here. Close to the moon. Which has a mass of 7.35 10 to the 22 kilograms. And capital R rate fixed radius of 1.737 10 to the 6 meters, 10 to the 6 million. And this asteroid is 1,000 kilometers above. Guys, 1,000 kilometers, is that also a million meters? So I can call this distance right here, maybe I'll call it D, is 1 million meters. Like that. So, guys, what's the total distance from the asteroid to the center of the moon? Maybe I'll call it lowercase r. Is it this many million meters plus that many million meters? That'd be 2.737 million meters. You guys can put that together. Okay. The radius of the moon plus the altitude gives you the total astronomical distance. Okay. Okay. And this has a mass itself of 100 kilograms. That's the asteroid. Okay. Make that an asteroid. And
That's very light.
asteroid is moving. And it also has an initial speed. So if the initial speed of the asteroid is 200 meters per second, we got to find the crash speed. Now, this kind of reminds me of what we did a few days ago with escape speed. I think it's going to be a similar setup. Because which pieces do you think we need to solve this? Yeah, this one definitely, and then this one. You guys think we can put these two together right here? These two? You guys think? Yeah. Let's do that. So okay, right here.
We're gonna go right.
I'm gonna set up sum of energy initial equals sum of energy final. I'll have some negative G M on R plus 1/2 MV initial squared. And then when it crashes into the moon, it has a different negative G M over R. I'll change this to a capital R because it's crashing on the surface, right? Okay, so this R and this R are different. You guys see that?
Yeah.
Okay. Plus 1/2 MV crash squared. That would be the setup, wouldn't it? Yes, sir. Okay, is there any question about where I got this expression from? So this initial speed is different from this crash speed, and this R is different from this R. Sorry there. Right, you guys said, you know what? We don't have we don't have enough time in class to finish this. But I think the most important thing is that you guys understand the setup and that you guys can plug in the numbers, right? You guys get it. So you could eventually solve for V crash. So okay, go ahead, staple all your work together and turn that into the grade tray. And I will put those points in the grade book.